We're going to have a look at connected rates of change and how to form differential equations. So let's just have a read through of this question and we'll do a quick sketch on this before actually setting up the differential equation. Liquid flows into a cylindrical tank at a rate of 100 pi centimetres cubed per second and leaks out of a crack at the bottom at a rate proportional to the depth of the liquid. The tank has a radius of 0.5 metres and its depth is increasing at a rate of 0.2 centimetres per second when the depth of the liquid is 5 metres. Form a differential equation for the rate of change of height. Define any variables used. Okay, so first of all let's consider what variables we will need to use here. We want to form a differential equation for the rate of change of height. So h appears to be a good variable to represent the height. And we should probably pick a unit because we've used metres and centimetres in the setup of this question. Most of it's in centimetres, let's choose centimetres. And the other variable which we're going to require in our differential equation is time. Again, everything appears to be in seconds, so let's use seconds. Okay, so we've got that. Now let's have a think how to actually formulate this problem. It says liquid flows into a cylindrical tank, so it's probably worth just a quick sketch of a cylinder, and radius was 0.5 metres. And we know that we have a height of h. Okay. Only trouble is that we know the rate at which volume is coming in. So we're going to need something that links volume to height. Volume is pi times radius squared times the height, and we know our radius squared, half a metre squared is a quarter. So we know that volume is pi h over 4. Cool. So now let's try and form a differential equation for this. I'll just move that there and rub off the previous stuff. So we were told that liquid flows in at a rate of 100 pi centimetres cubed. So that's telling us about the rate of change of volume. Okay, and again the water leaking out will be a volume change. So looking at this, we know that water flows in at this rate. Let's get it in focus. 100 pi, and it leaks out, so negative because it's coming out, at a rate proportional to the depth of the liquid. So proportional, I need a constant proportionality to the height. Okay, so that appears good, but the trouble is I've formed a differential equation for the rate of change of volume with respect to time. I wanted to know what it was for height with respect to time. I find the easiest way to actually think this through is to write down the one that I know. I know dv dt, and it's got a dt in it, so that's probably going to be helpful. I now need to find out what dh dt is. Again, I can use the chain rule. If I multiply this by by dh dv, we can see that the dv will cancel out effectively. Okay, that will leave me with dh dt. So write down what you want, write down what you know, and then think how can you use the chain rule to get rid of the one you don't want, in this case dv, and introduce the one you do want, in this case dh. Okay, now that all remains is to think how do I find dh dv? Well, from my initial sketching of the problem, down here, I wrote that v equals pi h over 4. From that, I can see that dv, dh will equal over 4. And therefore, I actually wanted dh dv. I can just take the reciprocal of that. Like we said, you can effectively think of this as a function, as a fraction, sorry. Cool. So now we know dh dv, we can put everything we know in here. 100 pi minus kh multiplied by 4 over pi. Okay? Simplifying this, that's going to give me 400 minus, what's it? kh, 4kh over pi. Cool. I now know that when I have a height of 5 meters, my volume is decreasing at a rate of 0.2 centimeters per second. So we'll now put that information in. This is going to help me find my variable k, my constant k. 400 minus, well, I could write minus 4k over pi, but 4 is a constant, k is a constant, pi is a constant. I can just replace 4k pi with some new constant. Why not? It's going to be much, much nicer to look at. Okay, finding out what a is. H was 5, sorry. I can see that I've got .399.8 over 5 is equal to a. I found my constant. I can now write down my differential equation. dh dt is equal to, using the simplified form, 400 minus 399.8 over 5 h. Okay, so just looking at the key steps that I've done there, start off, read through the question, define any variables that it's clear I'm going to need, including units. Then, if you've got some geometric shape or solid, just do a little sketch of it, get your bearings, and we realised we needed to link volume and height. So I wrote down a formula linking volume and height, simplified as much as I could. I then wrote down the differential equation using the information given to me in the question, dv dt. Realised it actually asked me for dh dt, so I wrote that down. And then said, well, I know the dv dt. How will I use the chain rule to introduce the variable I want, h, and eliminate the variable I don't want, dv? We got that, and then realised we could find dh dv using my previous work here. Simplified it, realised that 4k pi was just another constant, so rather than 4k over pi, just recall it a. Plugged in my initial conditions, or the conditions that I was told about. When it had a height of 5, volume was decreasing at that rate. I've just realised I missed the decreasing bit there. If it's decreasing, it must be negative. Careful of that. Okay, so if it's decreasing, it will be negative. Miss that one. Tidying everything up, put in your a, and you've got your differential equation. Okay, use the chain rule, check for negatives, don't make the same mistake I did, and simplify your constants. If you've got a whole group of them, you can replace them with one constant.